All right, so now let's go back. Let's look at our next part. Our next example shows the following pure rational expression or function that is x squared minus 3x over x squared minus 2x minus 3. Okay, so what we're going to do is, this is where removable discontinuities start to occur. And these are holes in the graph. So actual hole in the graph. And you can see it right there that there's a hole in the graph. And the reason why there's a hole in the graph is because there's an error as far as what happens at that specific x value. Okay, so for instance, let's first of all factor this and kind of go through it step by step. Notice how this was our standard form that was given, and then we turn this standard form by factoring it into this factored piece. They're still both a pure rational expression, but one of them is factored in orange and the other one is standard in gray. Okay, so and the reason why that's our first step is right here we can see a pair, a two of a kind, if you will. If there's a factor on the top that's the same on the bottom, well, we know we can cancel this to a form of 1. But with graphs of rational functions, that means when x is equal to whatever that is, okay, that would make it 0, that's where our hole is going to exist. Okay, so let me talk you through that one more time. We see a pair, x minus 3 over x minus 3. We know that that's going to be a hole in the graph. And if we want to know where that hole exists, well, then just set that thing equal to 0 and solve for x. This is where the hole in the graph will occur, when x is equal to 3. Okay, so think of it like x equals 3 is all along this line. And wherever it hits the graph, which is right here, that's where the hole in the graph is going to exist. Okay, everything else that's left over, then we're going to do the way we did these two pieces so that we can find the x-intercepts and the vertical and horizontal asymptotes. The same thing, x-intercepts, vertical and horizontal asymptotes. Okay, so again, this is after the hole in the graph has been accounted for. Okay, so we usually make x, as far as our denominators equal to 0, we usually make these our vertical asymptotes, unless that value makes the numerator equals 0 as well. In other words, this is that two of a kind that we were looking at over here. Then this creates a hole in the graph, which is a removable discontinuity. So removable discontinuity. And that means it makes this, otherwise this function right here could be continuous, but it becomes discontinuous because there's a break. There's a hole in the graph. So that's why we call it removable discontinuity. Now, if you plug in a value, an x value, and you get x over 0, then we know that the graph is going to have a vertical asymptote. Okay, but if you, vertical asymptote. But if you plug in an x value and you get 0 over 0, okay, which is kind of like what this is looking at. This x minus 3 over x minus 3, it is a form of 0 over 0. You're going to get this hole in the graph. Okay, this does cancel to a form of 1, but we also know that if x was 3, which is how we solve this location of where it exists, if x was 3, then we have 3 minus 3 is 0, 3 minus 3 is 0. So that's that 0 over 0 form, okay? That is important because what we were talking about from before of these three things here. 0 times a number divided by 0, 0 divided by a number, and the last one is, what is 0 divided by 0? In this context, with this unit, it's going to represent a removable discontinuity, otherwise a hole in the graph. Okay, so we're going to put that right here, a removable discontinuity. Oops. And that's that hole in the graph. But the table says error no matter what, so to know for sure, you have to factor. So you have to factor in order to find this hole in the graph. Okay, so for instance, this one right here that we were just seeing, it factored, this right here factored to x minus 3, and then it had x plus 1, x minus 3. So when you start looking at pieces, you first have to say, ooh, there's a two of a kind. That's where the hole exists. It's going to exist when the factor of x minus 3 is equal to 0. And we know that the hole is at x is equal to 3. Okay? And then what would be left over is this. And then from here, we would just graph it as normal. Okay? Where the top set equal to 0 gives me my x-intercept. Okay, so at x is equal to 0, when x is equal to 0, that's where I cross the x-axis. Shade that. And we see that right here. And then whenever I set my bottom equal to 0, I get x is equal to negative 1. This is going to be my vertical asymptote, which is what I see at x is equal to negative 1, which is right here. Okay, so a lot of things. Top x-intercepts, bottom is vertical asymptotes. Two of a kind is going to be the hole in the graph. And then the last thing that we would see is from the original equation, check this out, the top degree is 2, the bottom degree is 2. They're the same, okay? They're the same, and that's going to show us that what is that that horizontal asymptote going to be? Well, we come back over here, and we see that we're going to use Betsy. Betsy is when the bottom equals the top. When the bottom equals the top, let me highlight that for you right here. So when the bottom is equal to the top, then we're going to use our leading coefficients of the top and divide it by the leading coefficients of the bottom. Okay, so let me circle that real quick. And what will that look like over here? All right, so our original one was way back here, and since they're the same, then I'm now going to look at the coefficients. What are the numbers in front of that biggest degree? So this is just 1x squared, okay? And this is 1x squared. So if I looked at 1 over 1, well, then that's just 1, okay? And that's going to give me my horizontal asymptote. My horizontal asymptote will be y is equal to 1, because y is a horizontal line, okay? So let me go ahead and write that out and show that y equals 1 would actually be right here, okay? So you notice that this y equals 1 is different, and I got it from the original equation than the one that we did from up here, this x minus 2 over x squared right here, minus 1. So we graphed this one, which showed it's still approaching 0. Okay, so these bigger on bottom was y is equal to 0. It still approaches 0. It can go through it intermittently. But then this new one right here showed, because the exponents were the same, that you're going to have the coefficients in front. So 1 over 1 equaled 1. That's why this green line right here, if I were to put it right next to it, is y is equal to 1. Now, more practice, and I'm going to jump around. I'm going to skip some of them just so that this video is not super long. But nonetheless, we do need the practice to see all these pieces that are involved with these parts. Okay, so let's move on to our next part, which is, right here. Okay, so we're going to look at the graphs. So I'm going to skip a little bit. I'm going to look at the graphs right now. Okay, so that practice problems whenever it looks at factoring and stuff right now, for the sake of time, I'm going to skip that. You can look at your notes and look at the key. I'm going to go straight to the graphs. So for the following functions, determine where any horizontal asymptotes, vertical asymptotes, removable discontinuities occur. Okay, so first of all, first step, factor. First, factor. And these are in the pure rational form. Okay, so if I factor this, there's nothing to factor on top or bottom. It's still going to be the same. So x plus 4, x minus 3 is still the same. And now we can ask ourselves, let's go ahead and go through and find all the pieces that we're looking for. And so that we'll be able to list out all the attributes. And I'm talking about the horizontal, the vertical, the removable discontinuities, so on and so forth. Okay, so let's look at something real quick. If I were to list this out so I can systematically grab all the pieces and all the values that I'm needing, that I've learned thus far, this is something that we can look at. Okay, we can look at the domain. We can look at the range. We can also look at the zeros of the function. Okay. We can look at the VA and the HA. And the zeros are the X-intercepts. And then we can also look at the Y-intercepts. Okay. And the reason why I'm showing you, and then removable discontinuities. The reason why I'm showing you and just listing them all out is there's another acronym that you can use to help you identify what are all the pieces that I need to be aware of. What are all the pieces that I need to make sure that I do know? Okay, so here we go. If we look at, and there's a correlation between this is why I'm showing you this. I can look at the vertical asymptote. Okay, so that's taken care of. And I can look at the domain. That's taken care of. And now I can look at the horizontal asymptote and the removable discontinuity. And the range is going to be dealing with that as well. So let's come over here and we'll put range. Whoops. And let me just put that with like just an R. Okay. So the acronym that I want to basically show you that will help you kind of identify all the pieces. And I know I'm kind of like moving these things around, but it's really so that you can see the acronym kind of develop, is VAD hard. Okay. So let me highlight that real quick. We'll say VAD, and then we'll say hard is the, and you could say two R's. Let's do pirate, like hard. Okay, yeah, hopefully that was funny. But anyway, so, and then the zeros and the Y-intercepts are the other pieces. And the zeros and the Y-intercepts, I'm going to put them as just being up here. Let me show you where I'm going to put those. We'll say zeros and the Y-intercepts. So zeros, aka the X-intercepts, and then the Y-intercepts. So all of these pieces are what we're looking for. And now systematically, let's go through it. We first factored, which we have this. And then now I would look right here for the removable discontinuities. This is the number one thing that I would look for. I would look at, are there factors on top and bottom that are identical? If there aren't, then we can immediately say there aren't any removable discontinuities. The next thing that I would go to is the vertical asymptote, the denominator. When the denominator is equal to 0, that means at x is equal to 3, that's where my vertical asymptote is going to lie. Okay? And now, because of the things that we learned back here, that we can't divide by 0 because it's undefined. We can't divide by 0 because we could possibly get a hole in the graph. That's very, very important. Because my parent function was 1 over x, when x is equal to 0, we can't do that. We cannot divide by 0. That's a big thing. So that's why from here, after I get this vertical asymptote, I'll say, not only did our vertical asymptote shift 3 units to the right, which I can go ahead and just start drawing right now. So let's say that right here, 3 to the right, that's our vertical asymptote. But I also know that the graph exists everywhere else because that's the only piece. That's the only piece that would make me divide by 0. Okay, so at x is equal to 3, that's the only location where I would divide by 0, otherwise undefined answer, otherwise error out. That means the domain will exist everywhere else except for 3. So you could say the domain is all x's that are not 3, which some people prefer to do negative infinity to 3, union 3 to infinity. Okay, you could do it either way. That's just the shortcut way. And the reason why I have VAD hard is because you can see, oh, the vertical asymptote is 3. So the domain is going to be everything but 3. Now again, that's if there is not a removable hole. If there's a removable hole, well then your domain is going to come from accounting for this piece and this piece. Okay, it's anywhere where that denominator is equal to 0. Now, let's go back and look at the horizontal asymptote. We remember that the horizontal asymptote is looking at the original function. The powers of x are important, x to the 1, x to the 1. That means they're the same. So there's that back here. It's going to be Betsy. Bottom equals top, it's the coefficients. Okay, so if the bottom equal the top, that means this 1 equal this 1, then now we're going to go and look at the numbers in front of x. The numbers in front of x are these coefficient ratios, the coefficient over the other coefficient. Okay, it's not the powers, it's the numbers in front of the x, the coefficients. So this is 1 over 1, so we're going to say y is equal to 1. Okay, so let me go ahead and write that in or draw that. Y equals 1 is this horizontal line that the graph will approach at positive and negative infinity, but not hit. And then we have the range. So if y equals 1 is the place where it's not going to hit this y equals 1, then we can say the range is everything else other than 1. Or negative infinity to 1, union 1 to infinity. Okay, so now let's look at the zeros and the y-intercepts. The easiest one to find is the y-intercept because that's when x is equal to 0. And that means if I look at my original expression, if I put 0 in for x here and here, then I'd have 0 plus 4 is 4, 0 minus 3 is negative 3. So my y-intercept would occur at y equals negative 4/3. Otherwise, 0's x, negative 4/3 as far as a point. Okay, so you could put it like this, just saying that y value, or you could put it as a point. Okay, but negative 4/3 is like negative 1 1/3, which is about here. That's where my y-intercept would occur. And then now we know that the zeros is when the numerator is equal to 0. So we'll have it at x is equal to the zeros, or x is equal to negative 4. Otherwise, negative 4, 0 as a point. Okay, so at negative 4, 0, that's where I'm going to cross the x-axis. Now, if I were to plot more points, I'm going to get a graph, something that looks like the following. And notice that the graph right here will approach still the horizontal asymptote, and it will also approach the vertical asymptote. And then the rest of it is going to be up here, just a sketch, somewhere up here as far as where this would be located as well. Okay. Now, as far as graphing this and looking at other pieces, like you would actually plug in numbers and just get them. But for the sake of time, I'm not going to do that. Just again, the big takeaway is how did we find the vertical and the horizontal asymptotes from something that is a pure rational function? Okay. In other words, an expression that looked like it was just numerator over denominator. This is different from the previous videos of this week that showed in transformation form. Okay, so let me see. VAD hard took care of everything. We looked for the zeros, aka the x-intercepts and the y-intercepts. So we're good to go. That's pretty much the gist of it. Okay, so let's go to 2. Now I'm going to pick up the pace. I'm going to factor step 1. So the bottom is going to be x minus 5 and x plus 1. And this is in factored form. And immediately I see a hole in the graph. So I go to VAD hard. Okay. And then I'm going to look for zeros, x-intercepts and y-intercepts. So zeros. So we'll put zeros of the function, aka x-intercepts. And then we'll put the y-intercepts. So the y-intercepts will also be listed. Okay, so here we go. We just factored. That was step 1. Now we learned that we have a hole in the graph at x is equal to 5, because that's what would make this factor 0. Everything we're setting it equal to 0. Denominators, numerators, these removable discontinuities, and then we're solving where that existed. Okay, so again, this was my removable discontinuity. When I set it equal to 0 and solve, I get 5. So x is equal to 5 is where the hole would exist. And if I wanted to know what is that y value, then I can just plug in that 5 into x in the original function and see what would it spit out if I wanted to write it as an actual point. Like 5 in this case would spit out 1/3. Okay, that 1/3 would come as an answer after I plugged in 5 as the input. Okay, so nonetheless, that's where the point is going to be a hole in the graph. So after we found the removable discontinuity, we need to look at everything else that is left over. So everything else that is left over on the bottom and the top is going to be right here in gray. I have 2 and I have x plus 1. So let's go to the vertical asymptote. That means the bottom remaining pieces, not the original pieces, but the remaining pieces. Set all those remaining pieces equal to 0, which in this case would be -1. That's where the vertical asymptote is going to exist. So we'll go to -1, and let's go ahead and put, x is equal to -1. Okay. And now the domain. The domain will exist everywhere except for this place and this place. So we want to say x's that are not -1 or 5. So we're going to say from -infinity all the way to -1, because we're thinking like at -1 and 5, these are the only places that it will not exist. It will exist everywhere else if you were to looking at it like a number line. Okay, so let's take this and we're going to say union -1, to 5, union 5 to infinity. 3 different intervals to represent the first, second, and third interval, like on a number line. Now, another way that you could do this, you could just say, well, it's going to be everywhere except for those places. So you could say, or, we could have written it like this. The domain is x's that are not equal to -1 and 5. Okay, that's another way that you could have shown all of this for a domain. Okay, now let's look at the horizontal asymptote. The horizontal asymptote comes from the original expression. So I'm going to go back to the original and I'm looking at this. It's bigger on bottom, so I have y is equal to 0. So y is equal to 0 is going to be still my original x-axis is my horizontal asymptote. And then the range will be everything except for this place where that horizontal asymptote occurs, but also this place where that hole in the graph is going to occur. So this 1/3 you see becomes very, very, very important as far as how to list this as far as my domain and range. Okay, so again, if I were to think of it like a range, like y-axis, I would say at 0, it doesn't exist at 0, and also at 1/3. So if I did this, the way I did this interval over here, it would be from going from bottom to top, it'd be -infinity all the way to 0, union 0 to 1/3, and then 1/3 to infinity. Union and union, okay? And I made that just a little bit ugly. Let me fix that. So it was -infinity to 0, 0 to 1/3, and then union 1/3 to infinity. That's where the range is going to exist, okay? And if I were to graph this out, well, first let me get my zeros and x-intercepts. So the pieces that are left over, again, from this form up here, the pieces that were left over are going to be set equal to 0 so that I can find my x-intercepts. 2 set equal to 0, I won't have anything. I won't be able to find an x because there's not an x over here that I can get by itself. So we're just going to say none. Okay, and then the y-intercept is going to be, that's the easy one, putting x is 0, makes all those 0 out. So I have negative 10 over negative 5 is a positive 2. So y equals 2 or 0, 2, like a point. So 0, 2, there's that, but it will never hit the x-axis. And if I were to graph this out, it looks something like this. So we have a hole at 5 1/3, which is right here. So the graph is going to look like this. It approaches the vertical asymptote, goes through that y-intercept, shows that it does not have an x-intercept because of that none, and it approaches a horizontal asymptote of y is equal to 0 as it goes to the right. Okay, and approaches this vertical asymptote of -1 as it goes and gets closer to a -1. And then, yes, you could plot the other side, and you would have, I'm just going to do a quick sketch, pieces that look like this. Okay, also approaching the vertical asymptote and also approaching the horizontal